undergrad major here, business major, pursuing accounting and finance. So joining me is Luis Herrera, who is a biomedical engineering student at Johns Hopkins University. Together, we are here with Lilac Medical to present our flagship product, the AccuSpine. The AccuSpine is a low-cost surgical device used in spinal fusion surgery. The device is safe for patients, it is faster for surgeons, and it is cost-effective for hospitals. With AccuSpine, we hope to illuminate the field of spinal fusion surgeries. To begin, there are currently 500,000 spinal fusion procedures done in the United States every year. In this procedure, screws are placed into separate vertebrae and then connected using a metal rod to fuse and stabilize the spine. Spinal fusions are done in order to alleviate pain or to fix spinal deformities such as scoliosis, which is presented here on the left. Of the procedures done now, approximately 20% of the screws are misplaced and pierce the bone into the body, leading to reoperations into 5% of patients each year. Altogether, these complications cost the American healthcare system $3.5 billion per year. Now, this number is more important to surgeons and doctors than ever before because under the recent healthcare reform, hospital-induced complications will no longer be reimbursed through Medicare and Medicaid. This means that the cost of fixing these complications will come out directly of the pockets of surgeons and hospitals. This procedure is technically difficult and requires about 4 to 6 hours of surgery. The surgeon begins by boring a pilot hole into the vertebrae using a metal probe, which is our device. During this procedure, the surgeon uses constant X-ray to determine where the probe is going. This exposes both the patient and the doctor to constant radiation that are levels 10 times greater than any other procedure on the market. After the hole is made, the screw is placed into the pilot hole. The step is repeated for about 8 to 12 screws per surgery. The rod is then attached and the spine is aligned. So like we mentioned before, misplaced screws can have disastrous consequences. There are 2 types of breaches. First, there is lateral breaches, which go into the body and damage vascular systems. In the middle region of the spine, lateral breaches can puncture the aorta, which can lead to death. The other type are medial breaches. These go into the spinal canal and can directly cause pain, and in some cases, the screw can rupture the spinal cord and cause inoperable paralysis. This led to our invention, the AccuSpine. So the AccuSpine, how does it work? Using an electrical mechanical method, AccuSpine continuously measures changes in force coupled with a path identification algorithm to alert the surgeon by audio-visual feedback to a potential or impending breach, all in real time. For patients, it prevents the probe from exiting the vertebral body and causing harm to nearby organs, leading to a higher standard of care and reduced healing time. For surgeons, it removes the need for constant radiation and reduces the time of operation. And finally, for hospitals, it limits the cost of procedure by eliminating the costly imaging equipment and reduces the number of malpositioned screws which lead to reoperations. This is an inside look of our device. It is simple to make, simple to assemble, simple to sterilize, and most importantly, it is simple to use. When surgeons use this device for animal testing, they like the intuitive nature of our device. The surgeons and residents were able to begin using the device with minimal escalation from us. The simplicity of the device also allows us to produce a device very cheaply, which gives us a unique market position. Currently, Lilac Medical has filed provisional patents through Johns Hopkins University Tech Transfer, which is managing Lilac's IP portfolio. These patents protect the force transduction solution to pedicle breaches and the algorithms using the differential density calculation in our device. This allows Lilac Medical freedom to operate. As co-inventors, Louis and Amish, our other engineer, can have text transfer release the rights at any time since it is a non-government sponsored invention. We also have FDA connections so that we can gain clearance for the 510K regulatory pathway, which takes about 1 to 2 years. Finally, we are testing out the dead pig spine to see how our prototype works. The spinal surgery device market is an $11.5 billion market per year and is projected to grow at 5%. Our products are within a niche market that no other device has explored. This is a plot of the products that are available for accurate placement of screws. On the horizontal axis, we have the device's ability to provide guidance in pilot hole creation, with none on the left to significant on the right. On the y-axis, we have inexpensive products on the lower end and expensive products on the top. While the Dupuy Pro, which is on the left right here, right corner, is the most inexpensive, it offers no guidance and constantly relies on imaging techniques. In the top right, we have the Renaissance surgical system, which costs over $4 million and requires extended surgery time and constant recalibration. What AccuSpine is trying to accomplish is to invade the space in the lower right-hand quadrant, which is inexpensive materials with high guidance feedback. To begin with our marketing of our device, we already have an immediate consumer base at Johns Hopkins Medical Center. The current average reimbursement by the Center for Medicare and Medicaid Services is $90,000 per spinal fusion procedure. AccuSpine offers an unmatched feature enabling 15% reductions in operating time, which yield a projected savings of 10% per surgery. That is an average cost of $9,000 savings per procedure. While we start expanding to the nearby academic centers, which often utilize powerful imaging systems, AccuSpine can reduce complications, reduce operation time, and reduce radiation exposure for surgeons, while limiting the need for these expensive imaging equipment. We believe that the observation of these benefits at academic institutions will prompt additional research into the role of AccuSpine as a centerpiece of new and more efficient surgical protocols. To community hospitals, we will advertise our products as a key to reducing and preventing reoperations. Expensive imaging equipments are often unfeasible for such hospitals, remember, $4 million. And the AccuSpine serves as a cost-saving alternative, also offering exposure reduction and observed at academic institutions. As CMS is removing the reimbursement for hospital-induced infections and complications, more surgeons will be inclined to use AccuSpine to further reduce additional unwanted expenses. In addition, with CMS approval, AccuSpine will be able to be paid for through these reimbursements. To proceed on to the market, we estimated that our startup expenses are going to total $1.1 million, chiefly concentrated on research and development. Necessary legal expenses will also be handled at this time, such as full patent filing within 2015 and FDA regulatory approval. While this expense is not enough to finance a large-scale operation, it is enough to reach positive revenue streams in 4 to 5 years and indicate lucrative prospects to large-scale companies. Manufacturing considerations will also be taken into account, as well as medical device-grade packaging. Preliminary funding will be secured through various educational and government programs and grants such as NTEC and NIH. Outside private equity and venture capitalist investors will be approached for the bulk of the required startup expenses. These include active medical ventures and onset ventures. This is a graphical representation of our schedule. Currently, we're in the R&D stage, and we'll be done in 2015. Starting after that, we have our clinical trials, and then we are going to have FDA clearance in the first quarter of 2016. After which, we'll begin the initial sales of our product. In the future, we'll have the options to either exit the market or expand based on how the market is doing. Along with this, we are seeking a manufacturer to help us with clinical entry to push us from small clinical trials to large-scale manufacturing. This is where we can experience our optimal growth. Once we have secured adequate engineering testing, we will begin production of AccuSpine to satisfy 2 months of operations from our consumer base of 10 surgeons. At this juncture, we will have a window of opportunity to see where we can listen to clinical input and make modifications from a human factors ergonomics perspective. This is a graph of our projected revenue. As a baseline, one surgeon on average performs 100 surgeries per year. Our product costs $800 per surgery, and so on average, this gives us $80,000 per year revenue. In the first year, we already have a dedicated group of 10 surgeons at Johns Hopkins Medical Center to use our product. 10 surgeons at $80,000 per year is $800,000 in year 1. And starting in the second year of operation, we hope to expand our group of surgeons to 30 or even 40. So that makes our revenue go up to $3.2 million. In year 3, that's when we start expanding to academic medical centers. In year 4, we start getting to community hospitals and device distributors, which really handle the bulk of all spinal fusion surgeries. An interesting thing to note is that in year 5, we are predicting $32 million in revenue. 32 million is only 400 surgeons. If you consider the number of surgeons in an $11.5 billion industry, we are making profit of over $10 million at 5% market share. Imagine what we can be at 10%, which is where we envision ourselves in the future. Not only are we using a small group of surgeons to use our product, but we are expanding nationally. We are promoting our product in publication, science conventions, and new medical technology databases, as well as business competitions such as this one. In the coming months, Wildlife Medical will seek phase 1 funding and anticipates to break even within 4 to 5 years. We have based our financials on several considerations for our income and our expenses. Our income is based on sales of our product and the potential of licensing our technologies. We anticipate our profit margin will grow in subsequent years as manufacturing costs are depressed by sales growth. There is also potential to license our technologies in a number of applications, extending and stabilizing our revenue stream. Major expenses and marketing and operation expenditure, both of which are anticipated to increase with sales growth. We also take into account the taxes, such as the medical device tax under the Affordable Care Act, legal costs, and continued R&D. We will also invest in core research capacities to apply our technologies to neurosurgery and orthopedic surgery, so that as we mature in the spinal surgery market niche, we can exploit other untapped revenue streams. If our marketing strategy is successful, with positive surgeon feedback, we will seek additional investment and expand operations. If expanding operation is not a viable option, we will look for a buyout in the range of $45 to $55 million. While it will take our company an additional amount of years to reach a market capitalization, a larger company such as Stryker, with a greater exposure in the healthcare industry and with a greater profile of spine-related products, can easily reach that amount. The portal platform of our device also is applicable to trauma, hip revision, craniomaxillofacial, and dental surgeries, where there is the same safety concerns about placement of screws and bony structures that apply. The following are recent acquisitions by Stryker, as I just mentioned, just within the past 6 months. I want you to focus on the middle two. Stryker acquiring Pivot Medical shows how Stryker adds products which complement already existing suites. In addition, acquiring Patient Safety Tech shows Stryker's interest in software as well. Our device is within both of these categories, as AccuSpine is accompanied by its density algorithm, which can be utilized in a number of surgical procedures, both invasive and minimally invasive, that fall within Stryker's orthopedic product catalog. And that is just one example of a possible exit strategy. Aside from the two of us, we will have a wealth of experts that are giving us advice on our products and how we should enter the market. In addition, we have our clinical sponsors, doctors that are not only eager to use our device, but provide us with in-the-field ergonomics of our product. We also have a medical device and technology consultants which help us penetrate the market. Here we have taken several direct quotes from our interviews with orthopedic and neurological surgeons at Johns Hopkins School of Medicine. As you can see, they have clearly identified the Pedicle Pro as an instrument that is in much need of improvement. It is emphasized that if such a design were to be proven to be safer and more effective than the current options, it would be quickly adopted by the spinal surgical community. Pay particular attention to the last quotation. The mechanism that Dr. Pedagata requests is the exact mechanism that the AccuSpine provides. Through the use of both force transducers, our device provides not only breach detection, but more importantly, breach prevention through trajectory guidance and the surgeon candidates through the Pedicle Pro. This is an extremely powerful tool to benefit the outcomes of spinal fusion surgeries and presents an immediate advantage over all existing and potential competitors. In addition, we have submitted our device and business ideas to a few competitions, and these are some of our noteworthy results. Take a look. Ladies and gentlemen, we are Wildlife Medical, and we hope to illuminate the field of spinal surgery.
Panel, do you have any questions?
I just have one quick question. You talked about being the cash flow positive 3 to 4 years. That's after you start operations, which would actually be 7 years to 8 years from now, correct?
Correct.
That'd be correct, because that includes the startup expenses, the 1.1 million tranche.
Right.
So that's FDA approval and animal testing. Correct.
So in your pro forma, year one is actually 2018.
Yes.
First of all, I want to say that your written business plan was absolutely outstanding.
Thank you.
Very well written, no grammatical issues, and just very nicely done. And Louis, being a Johns Hopkins engineer, congratulations. That's really
Thank you.
good accomplishment. The product itself has sensors built into it. Is that correct?
Correct.
You're connecting this sucker to a computer that will then read out what's happening with that sensor. Is that kind of what you've got?
And so that's actually slightly incorrect. So this is actually a standalone device. So the surgeon doesn't have to use any other extra equipment. So everything's located on the device. It has the sensor that tells the surgeon where to go. Okay, it tells them by audio-visual feedback. So this could be beeping as well as the LEDs we have.
Okay.
Also, since it's simple to use, the surgeon really doesn't have to do any other training. It's basically the same device, just with extra features added to it.
Okay. You mentioned, Andre, in your presentation about how it is sterilizable, if I'm using a bad word or whatever, but you also talked about one surgeon doing 100 surgeries times $800, 80,000 bucks. So why does the surgeon, if it's sterilizable, needs to have a new one every time? Why are you creating a disposable product versus a more permanent product?
So that's not initial sterilization. That's not, the device itself is not sterilizable just because of the circuit. It can't go into the actual cleaning, so because of the high temperature. So the device itself is disposable. And you need the initial sterilization as well as the bipolar coating on the metals to make it feasible for use in humans.
Yeah, my question was kind of along the same. One of the testimonies we had, I think it was the third one down, Dr. Gokorslan
Good custom. Yes.
said every OR should have one. But again, it goes back to that question, you know, was he shown a prototype that is used over and over again, or has the product changed to where it's now disposable?
So we had various iterations. We first started with a standalone device that was reusable. But the problem was when we wanted to add the complex circuitry that we had, it posed a large problem. The gyroscope itself could not sustain that much heat, and other factors that we had in advance. So as a disposable device, one, there's the stigma of using a device that's been used already in another human. So that's one of the reasons we said, okay, we want to go for the disposable device. And the surgeons adopted that much more readily. It's also available right then and there. They don't have to wait if there's another procedure. The current standard that they have is a reusable device where it's only one within a suite. So surgeons actually loan it out to each other. And that just slows down the process. And that's what we did one ready and right now.
Okay, the next question is about the device again. Is this a microprocessor like an Arduino board?
Correct.
Is that what you use?
Yes, that's exactly what we're using.
Okay, so the programming is sort of minimal then to this, right?
Yes.
So it all is simply about density?
Yes, it registers a surgeon's cannulation force, so that's the force is applying longitudinally, and then also measures the torque. So that's when you saw the surgeon was turning it in.
Right.
So it measures that and then calculates the density based off of the cancellous and cortical bone. So cancellous is the soft sponge bone was on the inside, and the cortical bone was the harder outside shell. And with our algorithm, we've been able to determine that within 1 millimeter.
So it's really a plus or minus or a go, no-go?
Correct.
Is that what you're talking about? As long as I got a green light, I can keep pushing, and as soon as I have a red light, I stop?
Correct, and it's instantaneous. In our data, it's less than 100 minutes.
Hi. Great job on the presentation. A couple of questions. So, having that microprocessor control, if that were to fail, then that could present a serious safety issue with the patient, right? So, first, how do you account for that? And the second question I have is if you're aware of a 2010 patent for spinal probe with tactile force feedback and pedicle reach prediction, University of Minnesota?
So I guess your first question was, can you repeat the first question again, the first part?
About safety and fatal device data.
So the AccessMind is a class 2 medical device. So since it's not complete that the surgeon's going to be using this, he also has the other imaging equipment starting through Hopkins. Surgeons at Johns Hopkins Hospital actually just use the pedicle probe itself and minimal radiation, just because of the training they received. So if the fail-safe if the mechanism that says they're using too much force does not work, they still have the option to use intraoperative CT. So that's why it's still classified as class 2 and not class 3. And we're eligible for the 510K expedited pathway through the FDA. Okay, and then question 2, sorry. What was it again?
The 2010 patent on the tactile force feedback and pedicle competition.
So the Regents Minnesota filed an application, but I hadn't had the full patent go through. We've actually talked with them, and they've abandoned most of their surgical advice on that. They haven't been able to actually make it work with their device. So they have a lot of claims, and all those claims, if accepted, would stop our device. But from the constant revision, they started since 2006, they've lost a lot of those claims. They've actually gone down to only using a load cell, which is not what we're going to use in the device. So we're free to operate with our current patent.
Have you considered making this an appendage to, for example, a Da Vinci? You talked about the Renaissance machine a little bit, but perhaps the Da Vinci, which is a little more cost-forward. Any discussion about that?
The Da Vinci in surgical suite. So the Da Vinci is used for minimally invasive surgeries in OBGYN region. It's actually not used for spinal surgeries. So it would not be able to complement that, but our device currently complements the constant CT scan, the OR, and other imaging techniques, but it substantially reduces that amount by over like 10%. They don't have to take those 10 to 12 shots per screw. They can do maybe 1 or 2 depending on how confident the surgeon is in our device.
So this was a great job. Tell me a little bit about the team that you imagine being in place, say, in 2015, 2016. You've got some sort of the lead up to the FDA submission. Who's going to do those studies? What kind of, you're going to do it completely virtually?
So aside from me and Andre is currently CFO. He's helping us with the financial side. I work with more of the engineering side. I'm CEO. I'm working as CTO as well. So currently we have 8 students at Johns Hopkins Hospital aside from me. So I'm currently a junior, and we have other surgeons helping us, or the other students helping us with this. So currently our device is actually being used in animal testing right now. We started good bringing, but we have a full team of other engineers that are readily and able to help us with the device. Some are going to be graduating and might even continue to work full-time on this, and that's what we're going to go.
Okay, but in my experience, engineers don't deal with, I don't know what you're doing this on, rats or dogs, or, I don't know.
Yeah, so the current testing right now is animal pig spine for C models. Then we want to go into cadaver testing, and that's right before the FDA approval. So that hopefully, if everything goes well, that would be within 2015, beginning of 2016.